This lesson we're going to focus on sound. So mainly this is going to focus on the properties of waves and how they relate to sound waves. Okay, the one thing to remember here is that sound is a mechanical wave. So just like at this point we've been looking at transverse waves, sound requires a medium to travel through. Remember, medium is a substance, whether it's a solid, a liquid, or a gas. Okay, so it requires a medium. Unlike what we've been looking at so far, sound is a longitudinal wave. So it's basically the different type of mechanical wave we can look at. So this unit is only focusing on mechanical waves. Since it's a longitudinal wave, we already talked about those properties of compressions and rarefactions. So really a sound wave is defined as a transfer of energy resulting from the successive compressions and rarefactions of a medium because of a disturbance in that medium. So again, just basically taking the properties of a wave, it's created by a disturbance, and it creates areas of compressions and rarefactions, which again we compare to a crest and a trough. Alright, so sound waves travel through medium. What really happens is if you think of, say sound is traveling in air. Okay, the sound is energy that's leaving your voice or whatever the source is, and what's happening then is it's basically pushing the molecules away from their equilibrium point. Okay, so they're going to push the molecules. Molecules are then going to move, and they're going to collide with other molecules next to them. Then those molecules are going to move and collide with other ones next to them. So what happens is the energy is basically transferred through the collisions of molecules. Alright, we talked about this earlier, that sound is also known as a pressure wave. Why? Well, think about it when the molecules are colliding with each other. Alright, here you got one molecule that's going to come and collide. At some point you're going to get a spot where you're going to get two molecules that are right next to each other, and you're going to get some molecules that are spread out. So you're going to get areas where you have particles close, and you're going to have areas where you have particles that are far away from each other. Okay, so relating this to pressure and density, here we have a high density spot and a low. So we have a high density spot here and a low density spot there. So this is where the compressions and the rarefactions are seen. So that's why it's called a pressure wave. When we have the high density, that's going to create high pressure. When you have the low density, you're going to get low pressure. Okay, so it's basically a sound wave is a variation of pressure. Alright, so now let's look at the properties of sound. So the first property of sound, something we've already described it, is the wavelength. Okay, so the wavelength, defined as the distance between successive points on a wave. The simple definition when looking at a transverse wave was simply looking at crest to crest, or you could also go trough to trough. Okay, both these are seen as the wavelength. When looking at a sound wave, again, it's a longitudinal wave. So compressions are basically a crest, and rarefactions are basically a trough. So the same thing can be seen here. The wavelength is shown as the distance between two compressions or the distance between two successive rarefactions. The key thing here is successive, which means they're next to. So you have a trough, crest, trough. The two troughs are successive. They're next to each other. So that is the wave. Alright. Also with sound, we can also talk about the frequency. Remember that frequency is simply, when looking at units, is waves per second. Okay, so the number of waves in a given amount of time. So in terms of sound, what property does this relate to in terms of sound? Okay, as you increase the number of waves per second, what would happen? Alright, so how we relate frequency is to the pitch of sound. Alright, so you've probably heard sound being a high-pitched sound, a low-pitched sound. Really that relates to frequency. Okay, when you talk about a higher-pitched sound, that's going to relate to a higher frequency sound wave. Okay, down below I'm showing you a transverse wave just because it's easier to see. But notice here in a high-frequency sound wave that you have more waves per second. So if this is the period, if I draw this all the way down, notice on the top graph you have a whole complete wave. The bottom graph you have a half a wave. Okay, so you have more of a frequency up here. That's going to create a higher pitched sound. Alright, so what a higher pitched sound? Think of tuning forks. Right, tuning forks are basically created such that when they vibrate at a specific frequency. Okay, you have longer prongs, you have shorter prongs. Those are going to vibrate either at a fast rate or at a slow rate. Okay, so the kind of the properties of that are going to affect how fast it moves, and that speed at which it's propagating is going to create that frequency. Okay, so one that vibrates faster is going to create a higher frequency, a higher pitch sound. Right, so that's something seen. I don't know, think of like a female's voice compared to a lower frequency, which would be like a male voice, right? Higher pitch versus lower pitch. So frequency and pitch are what are really. Alright, so talking about frequencies and pitch, really the human ear can only withstand a certain amount. Okay, so the human ear can really pick up a certain amount of frequency. So that range is seen here. This is 20 hertz to 20,000 hertz, which is a pretty big range for what the human ear can pick up. Anything below 20 hertz is known as infrasonic, and anything above 20 hertz is called ultrasonic. Ultra being above, infra being below. Okay, can you think of an example of this? Well, a good example of ultrasonic is something like a dog whistle. Okay, I don't know if any of you guys have a dog at home, or maybe you've used a dog whistle. A dog whistle is usually a whistle that you could blow, and it almost sounds like nothing is coming out. You hear kind of a slight whistle, but it doesn't sound like much. But to the dog, a dog can hear in the human ultrasonic range. So they can hear above 20,000 hertz. So where it doesn't sound like anything to us, the dog whistle actually sounds like a lot to that dog. Okay. Another example, which is kind of relevant now, and it's something I've heard about, is the mosquito ringtone. I don't know if any of you guys have ever heard of it. Okay, but the mosquito ringtone is a ringtone that basically emits a very high frequency sound. Okay, so it's a very high frequency sound. If you think of the human ear as we get older, the sound that we can pick up in terms of our range of frequency changes. So this 20 to 20,000 hertz range is not the same when I'm 25 to when I'm 45. Okay, it changes. So they developed a ringtone that emits such a high frequency that adults cannot hear this frequency. Right? So it's in the ultrasonic range. It's such a high frequency that adults can't hear it. Now, don't try it in class because I can still hear that ringtone. Right? But it's basically making use of the sound spectrum and how humans can hear. Alright, now the last property of waves that we studied was the amplitude. Okay, so we talked about before that the amplitude is related to the energy of the wave. Right, the bigger the amplitude, the more energy it carries. The specific relationship was that amplitude squared is related to the energy. Okay, now when we look at a transverse wave, right, that's going to be a larger amplitude. It's going to carry more energy than a smaller amplitude. Well, how does that relate to sound? Okay, and really the amplitude of a sound wave is determined by the intensity of that sound. I think intensity, a high energy sound wave you would think would have more intense. A more intense sound is something that's going to be loud. So intensity is also related to loudness of the sound. Okay, so it's going to be a louder sound. So how we define intensity, really we're relating energy. So kind of above the below equation you can see that the more energy carried by the wave, the more intense the wave. Alright, so intensity is really defined as the amount of energy that source is emitting through a given area in a given amount of time. Okay, so it depends on time. Obviously, if it's emitting more energy at a quicker rate, right, that's going to be a higher intense sound. And depending on how far that sound will reach, okay, kind of talking about its range, that'll relate to the area. So looking at these two terms, you have the energy divided by time, which if you remember back to energy, that is associated with the power. So really the intensity of a wave is equal to the power of that wave, the energy per unit of time, divided by the area. So it's the power per area. Okay, so that's the intensity of that wave. And that also relates again to the loud. So here's kind of a range on the intensity and loudness of sound. You think that what is most damaging to our ears is actually the intensity of sound waves. the more energy that sound waves carry, the more harmful it is to the human ear. So just like frequency, the human ear can only withstand a specific range of intensities. Anything outside of this range is harmful to the human ear. Okay, so below is kind of a diagram or a table of kind of the intensity levels that we will face. Okay, so the lowest intensity level we can face is known as the threshold of hearing. Okay, that's the lowest one. Now, in terms of our equation, intensity is power per area. That's one of the things I didn't cover. If we look at the units, power is watts, and area is a distance times a distance, so meters squared. Okay, so you have watts per meter squared. So if you look here, the threshold of hearing in terms of our scale has a value of times 10 to the negative 12 watts per meter squared. Okay, so that's, if you think about that, that's a very low, 10 to the negative 12, that's a very low number. All right, and then kind of if I go up, the threshold of pain. Right, so that's where any sound at that level is going to cause pain to our ears. And notice that this intensity is at 3 watts per meter squared. So think about the range. You go from 10 to the negative 12, okay, to, in that case, 10 to the 0, right? So that's a very big range in these numbers. Okay, you have other ones in here, so like a rustle of leaves, that's 10 to the negative 11th. Notice these things kind of go by powers of 10, 10 to the 12th, 10 to the negative 11th, 10 to the 10th. Door slamming is 10 to the negative 4th. A siren at 30 meters, 10 to the negative 2nd. And in a jet airplane, that would be 100, which is 10 to the 2nd. Okay, so it's kind of a range in terms of powers of 10. All right, now we're kind of going to go into another intensity scale here in a second, but before I jump ahead, sound waves, and talking about intensity, sound waves are also said to be what are called spherical waves. Okay, if you think of what a sphere is, given some point, say the center, a sphere is a three-dimensional object about that center point, right? So if you think of any sound source, that sound is going to emit, or that source is going to emit sound, in all directions. So it can emit it in any direction as shown. Okay, if you think of like an X, Y, Z plane, right? It can emit sound in the X, it can emit sound in the Y, it can emit sound in the Z. It can emit sound in all directions. It's said to propagate radially in all directions. Radially, think radius. Okay? The diagram below will show you what a spherical wave is, meaning that when it emits a sound, it'll emit it to the right, to the left, up, down, in all directions in a sphere. Basically in all directions in the X, Y, Z plane. Okay, that's a spherical wave. Well, how do we determine the intensity of that spherical wave? Okay, and what this helps us to do is, given this, is now we can say, okay, what if I want to know if I'm standing a certain distance from a source of a sound? If I'm standing, let's say, the distance on the diagram here, R2, from that source of that sound. If I'm standing just a linear distance away from it, what would be the intensity of that sound? Okay, notice that power and area, yeah, that's nice, but it doesn't really give us a relationship between the intensity of sound and how far away I'm standing from a speaker or from any source, really. Okay, so this we can take the equation we did before. All right, intensity is power, and that fancy symbol there is just power divided by area. Okay, so taking it a step further, you have power divided by, well, what's the area of a sphere? If you look that up, the area of a sphere is 4 pi r squared. So this gives us an equation for intensity of a spherical wave, or another equation and I guess it's a more useful equation to calculate the power or the intensity of sound, which is power divided by 4 pi r squared. So again, P is equal to the power, and then R is the linear distance from that source. Okay, so it's the linear distance from that source. Okay, so we'll kind of do an example here in a bit, but you could be standing here. Here's the source. R would represent, okay, I'm standing 10 meters from that source. What is the intensity of sound I hear at 10 meters? Okay, so this equation here, make sure you jot down because that's an important equation when calculating the intensity of sound. Alright, so notice if you take if you kind of look back, and I'll show it again here, but the table of values for the intensity of sound, you should have seen that it ranged from 10 to the negative 12th all the way to 10 to the second power. Okay, where this 10 to the negative 12th was the threshold of hearing, and that's at lowest value, to 10 to the second was like a jet airplane. So it's a pretty, if you look at the powers of 10 and think of what those actual numbers look like, that's a huge variation. Alright, so a guy by the name of Alexander Bell developed basically a scale, probably something you've heard before, is now relating intensity instead of in terms of watts per meter squared, where we get those powers of 10, we are now going to relate it in terms of what are called decibels. Okay, decibel. Think of bell, decibel, right? It's a ratio. If you think of the term deci, using kind of our symbols and things in physics, a deci is something that's a power of 10. It represents 10. Okay. Think of like a decade or something like that, right? So basically he took a scale of 10 to the negative 12, 10 to the second, and related it in terms of powers of 10. To do that, he used a logarithmic scale. Okay, a logarithmic scale. So basically he's using the log base 10 of something. Alright, so he's relating log base 10 of intensity in terms of powers of 10 times 10 to the whatever, divided by the threshold. This I0 is the threshold of hearing. That's kind of the minimum value. So he's relating it to kind of the human ear. So times 10 to the negative 12th. So it's basically a logarithmic scale. And you might have to take a step back on how to actually perform mathematical operations using the log scale or using logs, right? But basically a log is just another way of rewriting something that's a power, or something that has an exponent, right? So something like 10 to the second we can rewrite in terms of a log scale, okay? So this decibel scale is basically beta. Beta represents, the symbol here represents the decibel level. 10 is just a value. This is log. In base 10, anything times log base 10, we just basically don't show the 10. This is whatever the intensity is, and we're relating it to the kind of that threshold. Okay, so we're basically setting a ratio between the intensity of sound we're facing to the threshold of hearing, and relating it to a different scale based on the powers of 10. Now, after I go through an example and things like that, it'll probably make more sense if you're not familiar with this type of math. Okay, so kind of looking here. Again, this is the table I showed before. Now, kind of looking here, notice on the right side you have powers of 10. This is the watts per meter squared side. And what we're doing is we're relating that to decibels, where this is kind of our threshold. This is our breaking point, right? Notice that is at 0 decibels. All right, and now the scale is related to that. If I jump up a power of 10, I jump up 10 decibels. Here I'm jumping up a power of 10. Jump up 10 decibels. Here I jumped up 2 powers of 10. I'm going to jump up 20 decibels. Okay. Again, 2, jumping up 20. Okay, so it's basically related to powers of 10, and that's all that it's doing, is basically getting rid of the power of 10 and looking at it in terms of a different scale, something that's more useful to us. Okay. So again, familiarize yourself with the equation 10 log of I over I0. And you may want to go back, and maybe in class you can ask me to kind of refresh yourself on how to solve log problems. Okay? Alright, so let's do an example. Alright, now I'm going to solve this problem on the kind of the next slide here. So if you want to write this down, write it down. Okay? The train sounds its horn as it approaches an intersection. The horn can just be heard at an intensity of 50 decibels by an observer 10 kilometers away. Okay, if you think of 10 kilometers, that's a pretty far distance. And a train sounds a horn. If you think of a train horn, it's pretty loud. You can actually hear that horn at a pretty far distance. Okay, so what we're going to try and find is this is a problem relating intensity. Alright, so we're going to have to use the equation of intensity, that I is equal to P over A. Alright, so we're going to try and use the intensity of sound. Now, the first part wants to know, what is the average power generated by the horn? Okay, so first thing we're going to solve for is power. And the next one, it says, okay, Now looking at, let's say, what is the intensity level experienced by an observer at an intersection 50 meters away? So now instead of looking at 10 kilometers, we're going to look at it, what is the intensity that someone 50 meters away would experience? Obviously, if you think about it, it's going to be a lot louder sound. That means a more intense sound. Okay? So make sure you jot this information down and solve it on the next slide. Okay, so what we have, our intensity of sound was 50 decibels. Okay, our initial distance for part A we're going to try and solve for what is the power of that sound. Okay, the distance R was equal to 10 kilometers, which is, I'll write in 10 times 10 to the third meters. I always put it in meters. Let me replace this. 10 times 10 to the third would just be 1 times 10 to the fourth meters. Okay, that's going to help me again. This is the linear distance. Okay, so what do I know that relates power, intensity, and distance? Well, and again, linear distance. Well, we had the equation that I equals P divided by 4 pi r squared. That's the intensity relative to a sound wave, a spherical wave, that relates intensity, power, and the linear distance. Okay, so thinking of power, let's kind of look at what we have. Well, we have intensity 50 decibels. Does that match what we have over here? Power, if you remember the units, is watts. R are units of meters, and meters squared. Okay, so do we have the units that match? Well, yeah, okay, we have meters in our R. Right, we have meters here. But decibels, are decibels watts per meter squared? No. So the first thing we need to do is take this 50 decibels and we need to convert it to watts per meters squared. How are we going to do that? Well, we need to use the decibel scale. Okay, so the decibel scale said that beta, which is the value of, or the intensity of sound in terms of decibels, is equal to 10 log of I over I0. Okay, so our decibel is 50 decibels equals 10 log of I over I0. So first thing you do, divide by 10, it cancels, divide by 10, we draw it over here, so you get 5 equals log of I over I0, and here's kind of where the tricky part comes in, where you have to remember your math. Alright, to get rid of the log, this is a log base 10. So what you do is you take the value on the left side, and that's basically representing a power of 10. So 10 to the fifth, that gets rid of the log, equals I over I0. Okay, so 10 to the fifth equals I over I0. Well, you should already know I0 is that threshold of hearing, so that's I divided by 1 times 10 to the negative 12th. Okay, so this is going to allow us to solve for intensity. So the intensity of sound is equal to 10 to the fifth times 1 times 10 to the negative 12th. Basically now that's just working with powers of 10, so you get 1 times 10 to the negative 7th. It looks like difficult math, but it's something you should easily be able to do, and that gives us units of watts per meter squared. Now again, we're trying to solve for power, so let's go back and look at the equation I equals P over 4 pi r squared. And we're solving for P. So P will equal I times 4 pi r squared. So let's plug in what we know. The intensity is 1 times 10 to the negative 7th. And I'm just going to kind of skip the units here. Times 4 pi times my distance r, 1 times 10 to the 4th meters squared. Calculate that. You can throw out your calculator there, and the power you should get after calculating that is 130 watts. Okay, so that's 130 joules per second. So that's calculating the power. All right, if you think about that, that's a pretty good amount of power. All right, now part B. Okay, part B now. Part B, we are looking for the intensity of sound when an observer is standing 50 meters. So the observer is at an intersection 50 meters away from the train. Okay, so what is the intensity at 50 meters? And what we're going to do is we're going to try and put this into the decibel scale. Okay, so what we solved in part A is we now know that the power of that sound, that emitted sound, is 130 watts. Okay, since we are 50 meters away, that is going to change the intensity, so we need to calculate the new intensity. So again, what relates power and distance? Well, I equals P over 4 pi r squared. Okay, so the power is 130 watts divided by 4 pi, and in our distance of 50 squared. Alright, and this is going to give you an intensity of, putting it in powers of 10, 4 times 10 to the negative third watts per meters squared. Now let's put this into the decibel scale, because this will make a little bit more sense then. So the decibel scale says that intensity in decibels is equal to 10 log of I over I0. Okay, so beta is equal to 10 log of 4 times 10 to the negative third watts per meters cubed, or meters squared, I'll skip that, divided by 1 times 10 to the negative 12th. Okay, so looking at powers of 10, 10 to the negative third, 10 to the negative 12th. Calculate that, put that into your calculator. You just type in 10 log parentheses that divided by that, and what you'll find is you'll get 96 decibels. Okay, which if you compare to the threshold of pain, the threshold of pain was about, in orders of 10, was 10 to the 0. Okay, this is 9.6 times 10 to the first. So this would probably be a pretty intense sound, one that would cause pain. Okay, so what to take this from this lesson is basically looked at the different properties of sound. Kind of the main problem solving idea was intensity. Okay, so make sure you take a look at your chapter problems looking at intensity and kind of familiarize yourself. You might want to go back and refresh your mind on log-based scales and how to actually calculate that math.